Okay, so we began talking about waves and we talked about some of the general properties that waves have. Uh, what was left from the introductory chapter was talking about the reflection and refraction and diffraction of waves. And for that, I'm going to take help from a video from YouTube. So it's a short video. We'll view it together, and hopefully, if the explanation is clear enough, I can leave the reading to you from the text for whatever explanation is given, and we can move on to the next chapter. So here we go.
To Moo Math and Science. In this video, let's figure out the difference between reflection, refraction, and diffraction. All these objects have in common they're all examples of the reflection of light. Welcome to Moo Math and Science and the difference between specular reflection and diffuse reflection. Not all objects reflect light the same way. So let's take a look at a difference between specular reflection and diffuse reflection. Specular reflection reflects all light which arrives from a given direction at the same angle, where diffuse reflection reflects light in many different directions. I'll show you the difference between these two by using a shiny object like this mirror and a dull object like this plastic. Up first, let's reflect light from a mirror which is very shiny. It will be an example of specular reflection. Notice that the ray always reflects at the same angle. Next, I have a dull object. Notice how the reflection always looks the same regardless of the angle. This is an example of diffuse reflection. During diffuse reflection, remember, the light is scattered in many different directions. With specular reflection, the law of reflection states that the angle of reflection of a ray equals the angle of incidence. So let's identify a couple of items. Here's the ray of incidence. Here's the ray of reflection. And a line perpendicular to the surface is called the normal line. And again, it's perpendicular to the point where the light rays strike the surface. Also notice that at different angles you can see that the incident and reflection are equal, and you can measure these from the line of normal. Normal is at 0, and the angle is at 30 degrees for both incidence and reflection. Here's another example. Normal is 0, and incident and reflection are at 45. This rainbow and sunset.
Alright, so that we don't really talk about specular and diffuse reflection in the syllabus, but that was about reflection, and the incident ray and the reflected ray. So that's something that will come up when we talk about light and what the normal is. So just the concept of reflection is something that you need to get familiarized with at this point, of course.
Our result of refraction and diffraction. Welcome to Moo Math and Science. Refraction is the bending of a wave when it enters a medium where its speed is different. For example, when this light enters this solid, you can see how it slows down and bends. Next, I have liquid. First, I shine the light without the water inside. I mark it with my ruler, and now when I add water, notice how the light bends. It slows down and bends. Now, diffraction.
So refraction is the bending of light, And so the thing he marked on the ruler is if the light were going straight through, right, you would see it following that black line on the paper. But what you can see is when it's passing through the water in this container, it's actually bending away from it. And so it's not going in straight. And so the bending of waves in general, when they are traveling through different media or through different depths in case of water, is called refraction.
Down and bends. Now, diffraction, it is the bending of light as it passes around the edge of an object or through an opening. The amount of the bending depends on the size of the opening. What I did was I wanted to try to create a very small opening, so I got two razors and put them very close together and shone this laser through it. Now here it is with the lights on, and now you can see how dramatic it is when I turn the lights off. Now, if you'd like to know what is happening as the light wave passes through the slit, here's what happens. It creates waves, and you see them in this pattern. So in summary, refraction and diffraction is the bending of light due to either slowing down or going around an object.
Right. Did that?
So,
Yeah, go
sorry.
ahead. Go ahead.
Reflection and refraction are the same thing. Like,
Reflection and refraction?
yeah.
Oh, no, not at all. Reflection is when light is bounced back. So it's not bending, it's bounced back.
Okay.
Right? The proper word for that is obviously reflection itself. But if you want to explain what reflection is, and in like the introductory chapter, we're not talking about light only, we're talking about waves in general, but obviously light is the best example for it. So reflection is when waves strike a surface and are bounced back. Refraction is the bending of waves moving through objects of different densities. For example, air and glass, or depth in case of water waves. And then you have diffraction. Give me a moment. Uh, so yeah, diffraction, as we said, right, it is the bending of bending and spreading of a wave. around an edge or through a gap, and how much it bends, or right, depends on the kind of edge it is, and the size of the gap. Now again, right, this is just to introduce you to the concept. If you take a look at the book, they've given you images as well, and they've mostly talked about water waves, right, because that's easier to show. They mention an instrument called the ripple tank. So that's an instrument that has water plus, a device to generate waves in the water. And then they have like an obstacle over here. And so when the water waves, right, they go in, they sort of like spread from here, or they bend, if it's refraction, and so they sort of bend. So it depends, right, what's going on. Uh, Now, if that concept is clear, at least we can move on to the next chapter, which is about light. Do you have any questions about the general understanding of these phenomena?
No.
Okay. So what we're going to do now is go to topic 3.2 and chapter 3.2.1, which is reflection of light. And so uh, right, first of all, they start off by talking about sources of light, and they say that all the reason we are able to see objects is because light from those objects enters our eyes. And so it is that light which is entering our eyes which is detected, and so we can form an image of the object. Now the question is, well, not all objects are giving off light, so how does that work? And so that brings us to, right, the difference between luminous objects, and these are the ones that give off light, right? So there's a source of light, such as a lamp, right, a bulb in a lamp. And then you got non-luminous objects, and for example the book that's besides you, the copy that's in front of you, or the pen that you're holding, and so they are not obviously giving off light. And so what they're actually doing is that they're reflecting light from another source. And so you just saw in that video, a book is not shiny, right? And so it's not giving like a bright complete reflection like the surface of a water or mirror or glass or metal would do, right? But the book is, when light hits it, it is reflecting it's spreading out the way that's happening. And so maybe, right, so, and that's one reason why if you walk into a dark room, even though it's got lots of stuff all around you, you're not able to make sense of what there is, right? uh, and because, right, I wouldn't say that there's no light. It's that there just isn't enough for to be detected by us, by our eyes, right? I won't say there's no light because we obviously have animals that are able to see really well in the dark, and we also have instruments to help us see in the dark, like night vision goggles. And so basically what they're able to do is they're able to detect very low levels of light and then produce an image out of that, even if it's not very clear. Right, it can at least distinguish that, oh, there is something over there that looks like, maybe a person standing or maybe a sofa or something. And right, so the non-luminous objects are ones that are reflecting light from obviously a light source. Light is coming in from somewhere. It might be the sunlight, might be a lamp, it might whatever it is, right? But and so you yourself are obviously a non-luminous object, hopefully. All right. And so what happens with luminous sources is the way they give off light is, right, in most cases it's electricity. So or some form of energy, right? So what they do is that they radiate light, when their atoms become excited, right? And excited here means, right, they go into a high energy state. And as a result of receiving energy, obviously, so they're receiving energy and they're going into a high energy state. And so for a light bulb, for example, right, the energy is coming from electricity, and right, when the atoms are excited, they give off their light, right, as we just talked about. Now, in these cases, the light is given off haphazardly. It's not focused. So haphazardly, right? Which basically means it's not focused in any one direction. And so that brings us to another thing which is called a beam. Right? And so a beam is, if I give you a proper definition for that, uh, right, it is, you know, rays of light that are parallel to each other and they are, focused in a particular direction. So, so a beam, right, are rays of, in fact, parallel rays of light focused in a particular direction. And so an example of a beam is a laser. And lasers are widely used. They are used, for example, in the barcode scanners at checkout counters, or they're used in industries to cut through metal or rocks, or even in medical procedures, right, for operations or for printing stuff. And so those are different applications of beams of light. Sorry, yeah, beams of light. Then there's another thing called a ray. Right?
Like it would be better if you could show a diagram of a beam.
A diagram of a beam.
Yeah.
Right, so I'll do that. A ray is how you represent the direction of the path in which light is traveling. Right, to diagrammatically represent the direction of the path light is traveling in. Or actually, right, any wave to show the direction which the wave is traveling. What you say is, right, you draw a line, and so, right, if this is, for example, a wave, and so what you do is you draw a line to show the direction of the movement, and so this line is called a ray. And so, right, for a beam, if I just show you, right, one example of a beam, if I show you the book, there are two diagrams, two illustrate, in fact, pictures, not diagrams. And so this is, right, a laser, which is also a beam, and it's being used for surgery. And so this light over here that you see, that's a beam. And then these are sunbeams, right? And so, right, you can see, this is something you can see when sunlight is coming through the clouds or coming through the trees or sometimes through the window even. And so that is a beam of sunlight. And so you can even see this if you have like a strong torch and you switch it on when it's really dark, in a dark room or in a dark hallway or even outside. And so you can sort of, if it's strong enough, you can see that beam of light traveling and illuminating the area. Does this help? Yeah. Hello.
Yeah.
Okay. All right. So going back, now, right, beams of light, I mentioned, right, that they are parallel, but that's not always true. So beams of light can actually be three different ways. They can be either parallel, which we talked about, or they can be diverging or converging. Right, and so for the first one, the parallel beams, right, they are parallel because the rays of light are all parallel. Right, so a beam is made up of rays of light, and so this is a parallel beam. right? Because the rays in that beam, all of these are individual rays, and so they're all parallel. A diverging is one, for example, right? You've got light spreading out. And so all these rays, they are spreading out. And so this is a diverging beam.
Only light can travel in beam and like rays.
I'll get to that just a minute. And then, right, they're converging. So they're sort of coming together. And so this is an example of a converging beam. Right, so it's not just light, right? Because light is part of the electromagnetic spectrum. And so other regions of the electromagnetic spectrum, such as radio waves and X-rays, right? And then there are certain mechanical waves, such as sound waves, can also, be made into beams. It just depends on how they are generated and how they are focused. So it is possible to have beams of sound waves or beams of X-rays, right? It's not just visible light. All right.
Yes.
Okay. All right. What else do we have now? Right. Speed of light. So they're not giving you a number for the speed of light over here. Basically, all that they're telling you under the heading of speed of light is that light is about 1,000,000 times faster than sound. And over here, we're talking about the speed of speed of light in air, right? Or vacuum. Well, not vacuum because sound doesn't travel through vacuum, right? And so the only evidence you need for that, if you've ever seen lightning and heard thunder, so thunder is the sound made due to that electric current discharging through the atmosphere, through the air. And so you always see lightning first, and you hear the thunder after a few seconds gap. And you can feel this even more pronounced if the lightning that you witnessed is, you know, further away from you. The closer it is, I mean, the difference for us would be fractional perhaps, but right, in any case, whenever we see lightning, it takes a few seconds for us to hear the thunder that comes with it. Right, and that is simply because light travels really fast, and compared to light, sound is much, much slower. And that's the only thing they're telling you about the speed of light. Okay. Now, then they're talking about, right, the reflection of light, which is sort of the topic of this chapter. And so there are 4 definitions that we need to introduce first. The first is, right, so reflection of light, for the time being, we are considering reflection happening on a plane surface, which means like a uniform straight surface, right? So on a plane surface, right? Plane meaning uniform, straight surface, right? And most likely polished. So we're talking about like a plane mirror. If you've ever been to some sort of carnival or amusement park or something, you know that mirrors can be of different types. You can have mirrors that are concave or mirrors that are uh, convex, right? Or you can have mirrors that are wavy or something like that. And so basically what we're talking about are the straight mirrors. These are the ones that we're talking about. These are plane mirrors. And so under that, right, you are shining a light on a surface. So this is a mirror. In fact, I can draw a straight line. And then I can draw a line coming in. So let's draw that at 45. Okay, there you go. So that's 45 degrees. And then it's hitting the surface and it's coming back at, how much would it be? 360 minus 45 would be 315. So 315, there we go. Perfect. Right, and so if, and we're going to draw a dotted line. Whoops. We're going to draw a dotted line over here. We're going to show this with arrows. And now we're going to label it. So this is a plane mirror. This is the incident ray. So the ray that's coming in. This is the reflected ray. Right? This is what's called the normal, right? Which was also explained in the video. And right, then you have the angle of incidence. So that is given with a lowercase I. And you have the angle of reflection, which is given with a lowercase r. Right? And so this is the angle of incidence, angle of reflection. And then let's talk about what these are. So first of all is the normal. And that is, right, a line which is perpendicular to the surface on which reflection is taking place. A line perpendicular to the reflective surface. Then you've got the angle of incidence. And that is the angle between the incident ray and the normal, right? So the angle between the normal and the incident, so not the outer angle. Between the incident ray and normal. Then you have the angle of reflection. And right, that's the angle between the reflected ray and the normal. Oops. So, right, these are the things that, right, and then we finally come to the law of reflection. So I'll go to a new page for that. It's pretty simple, based like if you've understood everything we've talked about so far. So the law of reflection states that the angle of incidence is equal to the angle of reflection. That's all the law of, you know, reflection states. And so when you have a ray of light falling on a plane surface, on a plane reflective surface, on a mirror, right, whatever angle, and so again, right, so that was very well demonstrated in the video we saw right at the beginning, and he mentioned that angle of incidence and angle of reflection with, you know, that circle he had made, clearly showing the degrees, the angles. And so that should always be equal if it's falling on, right, in fact wherever it's falling technically, right, unless diffraction or something's happening. Okay, any questions so far?
No.
Okay, so to quickly go through this, right, they mention something that's called a periscope. And a periscope is basically a device that has two mirrors installed at 45-degree angles. And again, right, it doesn't feel like it needs a lot of, you know, explanation on the whiteboard for some reason. And so basically this is a periscope, as you can see. So they've explained it over here. And so they've got this device with two bends. They've got a mirror over here at 45 degrees and a mirror over here. And so light comes in, it bends down at 45. Well, it actually bends 90 degrees because angle of incidence is 45, angle of reflection is 45. And so the total angle the light has been, you know, reflected is 90 degrees, right? So in the example, we also, right, made the light, the angle between the total angle between the incident, total angle between the incident reflected light is 90 degrees. And so it comes down, it hits the other mirror, which is also at 45 degrees. And so again, you've got a 90-degree reflection. And then, you know, you can view it. So you can view things that are either over an obstacle or high above, right? And right, that will, you know, so here's an example. If you're sitting in a crowd and you take this makeshift periscope, so you can see above the crowd, sort of like, you know, something. In submarines they use, you know, prisms, so that's, you know, more elaborate, that's more accurate, it has perhaps greater definition or resolution or distance that it can cover. And then over here they mention, you know, how you can make a periscope at home. Right, I'll stop here. There's a bit about plane mirrors and images, so we'll start from there to the next class, and then, right, we'll take it forward. Any questions?
No.
All right, so I'll see you next time then, inshallah.
Okay. Allah Hafiz.